Okay, so in this video, we're going to be calculating the terminal velocity of an object in free fall. So to set the stage here, we have a person on a cliff face holding an object of mass m. That person is going to drop the object over a height h, after which the object is going to hit the ground, which is defined as y equals 0, with y positive up. To go through some of the knowns of the problem, the object of mass m is 350 grams. Lunar gravity is given as approximately 1.625 meters per second squared. The height h is given as 400 meters. And the drag equation is given as kv squared, with k equal to 0.0002 newton second squared per meter squared. Now it's worth noting that this k value is not universal. The value of k is going to be a function of the shape of the object and the density of the medium through which the object moves. It's not a universal value, but for this problem, it's given, so we're going to use it as given. Some of our fundamental assumptions, we're going to neglect buoyancy. The starting velocity of the object is 0, meaning the person drops it from rest. And we're going to only be dealing with unidirectional motion, meaning the person's not throwing the object such that it's traveling along a parabolic trajectory. The person's simply dropping the object vertically from rest. So the first thing we would do here is a free body diagram. So free body diagram of mass m. With dynamics problems, you often don't know what the directions of the forces are, so you can just give it your best guess and the math will work it out at the end. So if you assumed an incorrect direction of the force after you solve for it will come out as negative. We're going to now write our first governing principle, which is Newton's second law in the y direction. So sum of the forces in y is equal to may. So sometimes I have people asking why we don't really ever assign a sign to this side of the equation. For example, why don't we ever really write negative may or assume, a negative acceleration when we can kind of physically intuit that the acceleration is negative? The explanation is you can assume a negative acceleration. However, it tends to complicate the problem pretty significantly. What I've learned is one of the best ways to proceed with Newton's second law is to simply define with your coordinate axes a positive direction, as we've done here, positive up, and then assume that AY is positive as defined by the direction that you defined as positive. So in this case, I'm assuming positive AY. Now, because it's a scalar component, just like the forces, the sign of AY will work itself out in the math at the end. So if I get a negative acceleration, I know I assumed the acceleration as up is incorrect. It's actually down, which just so happens to align with my negative y-axis. So it's very intuitive and it aligns with the geometry as we've established in the problem. Give your best guess for the forces on the left-hand side of the equation, and then set those equal to positive may. So we have FD minus W equals may. One of the ways we can simplify this problem is by remembering that the acceleration is just the time rate of change of velocity. So we can express this as m dvy dt. There we go. dvy dt can be expressed alternatively with the chain rule. Now the chain rule allows us to write dvy dt as dvy dy dy dt. So in this case, you can say, oh, well, if I treat them as fractions, I can kind of cancel them out, and then I'm just left with dvy dt. That's a way to remember the chain rule. That's not really what you're doing, but that's a way to remember the chain rule. Remember, derivatives are not fractions. You typically cannot treat them as fractions, but this is just a heuristic memorization tool. The time rate of change of y is just the velocity in y. Then we can simplify this as dvy dy vy. Now, I think we've kind of emphasized enough that this is unidirectional motion, so to kind of save some writing time, let's drop the subscript y. What we're going to try and do here is take this derivative and get all the terms in v on one side and all the terms in y on the other. Let's rewrite that. dv dy equals kv squared minus mg over mv over kv squared minus mg, and that's dv equals dy. So we're going to integrate this side, and we're going to integrate that side. So mv over kv squared minus mg dv. What we're going to do here is something called u substitution, as you might remember. Let's define a u. We'll say u is equal to kv squared minus mg. And then we'll say du dv is equal to 2kv minus 0. The derivative of a constant is 0. So now we have to bring this whole integral into u space. We start by saying the integral of 1 over u, mv dv. We can play a little trick here by saying 1 over u times 2k over 2k times mv dv. We know that du is equal to 2kv dv. So what we can say here is that this is equal to the integral of 1 over u, 1 over 2k still here. We'll bring the m out here, and then what we have is 2kv dv. But we know that that is equal to the integral of 1 over u, 1 over 2k, m, 2kv dv is du. Now, what we can say is we have this integral as m over 2k times the natural log of the absolute value of u plus some integration constant, c1. Now, it's important to remember that that integral, the integral of 1 over u, is the natural log of the absolute value of u. That's required. That absolute value is required to ensure that the natural log function is defined. So we're going to have to use some physical intuition to get rid of that absolute value because it kind of screws with some of the other simplifications we want to make in the future. Natural log of, what did we define u as? So it's the absolute value of kv squared minus mg, okay, plus some integration constant. Let's write it in blue. Y is equal to the integral of mv over kv squared minus mg with respect to v, right, which we have is equal to m over 2k, natural log of the absolute value of kv squared minus mg plus some integration constant c1. Okay. What do we know about the terminal velocity? The terminal velocity is the steady state speed achieved by an object in free fall. Once an object achieves its terminal velocity, barring external influences, the object will stay at that terminal velocity perpetually until something hits it, basically. So what we can say is the terminal velocity is the highest speed that an object will achieve. Okay, so what that essentially means is that the drag force, which is proportional to the speed squared, this kv squared right here, we know that from Newton's second law, what that means is kv squared is starting at 0 and slowly ramping up until it equals mg, at which point the object has no net force acting on it because the drag force is equaling the weight of the object and the object has reached terminal velocity. So what does that mean mathematically? It means that kv squared should always be less than or equal to mg. This quantity should always be negative or 0. So the absolute value is always acting on a negative or 0. So we can say the absolute value of kv squared minus mg, where we know kv squared minus mg is always negative, y equals m over 2k, natural log of negative kv squared minus mg plus c1. We know that is just m over 2k, natural log of mg minus kv squared plus c1. Just really quickly again, since we know that the drag force is always less than or equal to the weight, kv squared is always less than or equal to mg. And what that means is this quantity is always negative. So if this quantity is always negative, then the absolute value of this negative quantity is simply the negative of the quantity. And what this says is, if you give me the velocity of the object at any point in that travel, I can tell you exactly where it is. And that's only defined for kv squared less than or equal to mg. If kv squared is greater than mg, it's a non-physical situation, kind of the equivalent of doing a kinematics problem and getting a negative distance. So it's only this function right here is only defined for kv squared is less than or equal to mg. So at this point, it would be kind of nice to be able to express this as a velocity. Let's start working through some of that algebra. Actually, no, we'll save this algebra for another video, I think, because it's getting a bit long. I'll see you then. Okay.